Hey guys, it's Finn. In this video I'm going to talk about NEAT. It's short term for Neuroevolution of Augmenting Topologies, and it's one of the most interesting algorithms that I've seen in the past, and it's incredibly powerful. And I'm going to go through the algorithm step by step and explain each step. In the future videos I'm going to already also code that, but this is going to take a little bit longer because that algorithm is pretty complex and not that easy to code. And like in the past few weeks, I've read those papers and I've asked stuff in the internet, and I tried to code it, and I eventually got it to work. But I'm not 100% sure if my implementation is correct. But I tested it on a few games and it works pretty well, so I assume that I've implemented everything correct. But the thing is that if you read the paper, there are some things not quite explained. So some things that I'm going to show you is based on what I would do or what would make sense. So just like watch and enjoy the video. What I will do is I will explain the term first, the neuroevolution of augmenting topologies. And what I will do is I will put it into the bottom left corner in red, and I'm going to explain each word. So let's start with the evolution. We had evolution before. We had genetic algorithms. We had evolution, and we had like 3 steps usually. We had the selection, the crossover, and the mutation. And this is exactly the same in NEAT. We are going to have exactly the same steps in the same order. And I'm going to explain each step later on. We also have neuro in the word neuroevolution. Neuro stands for like neural networks usually. And we have already talked about neural networks as well. Genetic algorithms can be used for nearly anything, not only for neural networks, but NEAT is only for neural networks, or I haven't seen any counterexamples. So we have had networks before, but right now we are not going to talk about those kind of networks because we have a term in the name that is called topologies. And topologies is like how many neurons, how many layers, and how many weights and so on do we have. The thing is about NEAT, it's going to evolve those structures. It can evolve those weights, but as well as how many layers do we have, how many neurons do we have. And actually we are going to not have any layers anymore. We are only going to have connections, and we're going to have nodes or neurons. I'm going to refer them to as nodes in the future. So how do those networks look? There's a video on YouTube which applied the NEAT algorithm to Mario, and it's pretty cool. I put the video in description, and it's very cool to see how it evolves and learns the game. So the last thing that we have is augmenting, and the reason for that is what you need to know is the smaller the network, the faster it will find a solution. The thing is, if the network is too big that we choose to begin with, it might take too long. If it's too small and it cannot change the topology, it might not be a good solution. So the idea is to start with the smallest network possible and mutate connections and so on to increase the topology of the network, to increase the amount of nodes and connections. And therefore, if we haven't found a good solution, we're going to increase the size. And this is like, we're not going to do this manually. This is like part of the algorithm, and we're not going to implement that, but it's going to happen anyways. So this is the word itself explained. But what I mean with augmenting is we will start with the smallest possible network. It's like we're going to have the input nodes and the output nodes. That's fixed. We like cannot add input nodes or output nodes. But what we, for example, could add is a connection between 2 of those. Or what we could also add is we could add a node on one connection. So we could like divide this connection in the middle, add a node, and do something like this. And this node could also be used on for creating connections between, for example, this node and the first node in the input layer, like this. A very important thing about this is encoding. What we did before is when we did, so for example, the mutation or the crossover, we just took like the weights array and put them on top of each other and choose each time we have chosen a random value of either the first array or the second array, and we got some crossover. This doesn't work because we don't have fixed topologies. We don't have weight arrays or something like this. Everything is going to be a little bit more complex. So what we have is we have genes, and how they look is something like this. We have two different type of genes. I hope I'm pronouncing them that correctly. I hope it's pronounced gene. I'm not sure about that. What we have is we have like one genome is a set of genes, and we have two different type of genes. We have node genes and connection genes. And what we store in one node gene is the identification number of that specific node. Usually we start at the input and output nodes. So we have like in the top right, we have 1, 2, 3 input, 4, 5 output, and 6 is the hidden neuron. And after that, each hidden neuron is going to have a new number. We also have connections. In this example, we have 3 connections. And what they are labeled with is the connection at the node that it's coming from, the node that it's going to, and it's going to have something that's called innovation numbers, or a innovation number. And this is incredibly important. Innovation numbers are the reason why need works the way it works, and why it can do very efficient crossover. Identification or innovation number is pretty much a number that determines when a connection has been created. And yeah, well, that's pretty much it. You assign those innovation numbers to newly created connections. And each time you create a new connection in any network, so these are shared between networks. If you have a network that creates a new connection that doesn't exist in any network or in any genome, you're going to add a new connection with a new innovation number that is incremented over time. If that connection already exists in any other genome, you're going to set it to the same identification or innovation number as in the other network. And this is really important to do some good crossover. And the reason for that is the following. Crossover works like this. We only need to cross over the connection genes because we can derive the node genes from the connection genes. So in this example, we have the first network and the second network. Like we have always the same input and output size. It's not necessarily a output size of 1. This can be like any output size. So we have our 6 connections, and in this example, over here we have 9 connections. So what you can see is this network has 1 node more than this one does. But for example, the connection from 2 to 5 is the same connection as this connection from 2 to 5. So what we will do is, and you can see that it actually has the same identification number. Like the identification or innovation number is on the top. It's 4 for this one and 4 for this one. So this is like the same connection, and this is important. If they would not have matching identification numbers, everything would fall apart. So this is really important. So the next thing that we need to do is we are going to align them by taking their innovation numbers, something like this. So parent 1, we're going to take the connection genes of parent 1, and we're going to put the connection genes of parent 2 right under, and we will compare them. Like, for example, each matching connection gene, we're going to choose a random gene. So the offspring is going to have a random, is either going to have this connection or this connection, and usually these connection genes are displayed with the information of the innovation number and the node that it's coming from and the node that it's going to. What we are also storing is the weight that this connection has, and a Boolean value that determines if this connection is enabled or not. This is only important for the calculation, but this is kind of used for like the network can identify connections that it doesn't really need and remove them later. without like actually removing them, we're just going to disable them. They're like they're still existing, but they're like disabled, so we're not using them anymore. Okay, so what we will do is we are going to like choose a random gene if both of them have the same identification, or if both of the parents have that specific gene. If only one parent has that, we're only going to take it from that parent. So what we end up with is probably something like this. And there's a term for these genes at the end. We have excess genes and disjoint genes. And excess genes are those genes that are like at the end, and disjoint genes are those that like do not have a matching counterpart in the other parent, but are not at the end. And the reason for that is, if we say parent 1 is fitter than parent 2, we are going to ignore the excess genes of parent 2. So if we say parent 1 is fitter than parent 2, this would not be the offspring. The offspring would be without the gene 9 and 10, because they're excess genes of parent 2. However, if parent 2 would be more fit than parent 1, we would have 9 and 2 included, because they're excess genes, but they are inherited from the more fit parent. So what we would end up with is a network that would look something like this, that has the features of parent 1 and the features of parent 2. Now let's come to the mutation step, which is actually pretty simple. It's probably the most simple thing about the algorithm. And usually, if you look for the algorithm on the web, you will find 2 different mutations. But actually, there are 4 to 5 different mutation types. You have already seen 2 of them. So the first is we mutate a link. This is pretty simple. We just add a new link with a random weight between -2 and 2. The next thing is we can add a node at any random connection. So we could divide it, and the weight of the first connection is going to be set to 1, and the second is going to be set to 0, like to the weight that it used to be. Usually we're creating 2 new connections, and the old one is being removed. So if those connections have never existed, or actually they have never existed, we are going to create a new node. So we're going to set a new identification number to that specific node, because no other network can have possibly created those nodes, because it's like a randomly chosen node. This is like a little problem in Neat, but we just need to stick with that. So this is going to be a new node in the global nodes array, however you want to call it, with a new identification number, and we're going to have 2 new connections, and these are also going to get a new innovation number. However, if we create a new link, it might happen that this link has already been created, because these nodes are known for every other network, or for every other genome. So this might get a innovation number that already exists, because this weight might also this connection might also already exist somewhere. So the next mutation that we have is we can enable or disable connections. This is like we take a percentage of connections that we want to enable or disable, and we will just like choose randomly. We will choose some connections randomly, and we're going to flip. If they are enabled, we're going to disable them. If they're disabled, we're going to enable them. The fourth mutation is the mutation weight shifting. So, for example, we could take a weight and shift it either to the top or to the bottom. Usually we just take the weight and multiply it by a number between 0 and 2, but this is like up to the how you want to implement that. And the fifth mutation is very close to this one, but the fifth is we're going to simply choose a completely new random weight. We could not reach this weight by shifting the 1. We actually need to choose a new random weight between -2 and 2. So now comes the hardest part, I would say. I think that was for me the hardest thing to understand. and it's the selection part. So what we do is, I try to do it with some fancy animations, but I think they kind of fade, so don't be too hard with me in the comment section. Let's say we have 9 different genomes, and each of these did get a score in the world. These scores are like a score for their connection genes and node genes, how good this network performed in the world. So what we do is we're going to do some speciating. What we do is we will take the first, we'll go through every single genome, and we are going to have like our species on the right. We have no species yet, but what we do is we will take the, let's say we take the first, and we're going to run through all the species and check how good it matches into that species. So there's no species yet that matches our current genome, so we're going to create a new species. So we will take the first genome, put it to the right, and create a new species. Then we will take the second genome and compare it to the we will run through all our species, we only have one, and we will compare if it's matching into our species by comparing it to the first element in that species. So we will take 2, run through all our species, we only have one right now. We will compare it to the first element. If it's called the distance between 2 genomes is below a certain threshold, we're going to add it to that species. Otherwise, we're going to create a new species. So I just said that the genomes are pretty close, and if I say they're close, I'm not saying that the numbers are close. I'm saying that like the connections are very equal. The weights are kind of equal. We don't have a lot of excess and disjoint genes, something like this. So there's a formula for that, which I will show you in one of the future videos. Now let's take the third genome, and we're not talking about score right now. The score will come later. So we will compare the third genome to the first. We will calculate the distance to the first genome, and we will see, okay, well, this does not quite match. So we need to create a new species, because there's no species that matches our genome. And I'm going to just simply shift it to the bottom, and right now we have 2 different species. Same for the fourth. We are going to compare to the first species by comparing it to the first genome in that species. We're going to compare to the second species by comparing it to that specific genome, and if it doesn't match as well, we're going to create a new species again, and hopefully we end up with something like this. So it's not lined up perfectly, but I hope you can ignore that. So what we will do then is we have our species. So I think it's called species, just simply species. We have our species. And what we will do is we will sort the genomes in our species by taking their score. So we are going to swap 4 and 5, and we are going to swap them at the bottom. So we have every species sorted. And what we will do then is we will kill some of those genomes. And those that we are going to kill is we are going to say, okay, we want to have, let's say, 50% killed. What we will do then, of each species, we are going to kill exactly 50%. So that means that we would kill. I think did I make? Yeah, I made that. I made it. So of each species, we are going to kill 50%. But the good thing about this right now is that a genome that has been really bad can survive the selection, and this is really important. The reason for that is that we're not only selecting those genomes with the highest score, we are ensuring that there are also genomes alive that have a different architecture. So look at the top. We have two genomes of this type. They both scored kind of badly, but one of them survives. So by creating those species, we are ensuring that also bad scores are going to survive, and we are going to have different types of, or we are going to have different topologies in the next generation. And this is really important. It was a huge problem in previous genetic algorithms that you might have, like delete topologies that might be good in the future. And what we are doing is we are going to tell this, like we are going to pretty much tell this, okay, look, you will survive. You're not really good, but we are giving you a chance to improve. Maybe your topology is really good, and maybe your topology is like the best, but you need some innovation. So this is like we're giving space for innovation, so that we're not directly killing bad innovations. Or like it could happen that a good innovation happens, but it has a really bad score, and only over time it will eventually be good. And yeah, this is like the idea of selection, and this is really important. This distance function is pretty simple. You can find it everywhere in the web. I don't have it in my presentation right now, but I'm going to show it to you in one of the future videos. And I will also start coding this in one of the future videos. And if you like this, just click the like button, and please tell me, give me some feedback. How did you think was this presentation made? And I hope to see you in the next video.